As soon as the smaller disk is lowered onto the larger disk centered at O, we choose the regions on the smaller disk which are diametrically opposite to one another and name them A1 and A2, centered at O prime. Now, the regions A1 and A2 of the smaller disk acquires the velocities of the larger disk at those points. We name them V1 and V2. Now we want to find the direction of those acquired velocities. We know that the larger disk rotates with angular velocity capital omega counterclockwise about O. So V1 is equal to OA1 omega and V2 is equal to OA2 omega. So V1 is perpendicular to OA1 and V2 is perpendicular to OA2. Hence we get the velocities V1 and V2. As the smaller disk is lowered, the frictional forces will be along the motion of the regions, that is, along the direction of the velocities. Hence F1, the frictional force on A1 is along V1 and the frictional force F2 is along V2. And as the disk is uniform, hence F1 is equal to F2. Now, a net torque due to the frictional forces at both the regions about O prime will be generated, where O prime is the center of the smaller disk. The torque will make the smaller disk rotate about its axis. But in which direction? Well, as the arm L2 is greater than the arm L1, from the diagram, the torque due to F2 will be greater than the torque due to F1. Hence, the smaller disk will rotate about its axis with an angular velocity omega in the same direction as the larger disk. Now, due to this rotation, the two regions acquires relative velocities v1 prime and v2 prime, where v1 prime is equal to v2 prime is equal to omega r. So v1 prime is perpendicular to r and v2 prime is perpendicular to r. So we have here v2 prime and here v1 prime according to this equation. Now let's find out the direction of the frictional forces. As this is the only force propagating the smaller disk, it must be along the new velocity vector. Let this point be a1 and this be a2. Let this point be a and this be a prime, where a is the point just below a1 on the larger disk and a prime be a point just below a2 on the larger disk, where a1 and a2 are the points on the smaller disk. So if a1 is a point on the smaller disk touching a point on the larger disk, we get velocity of a with respect to a1 plus velocity of a1 with respect to o is equal to velocity of a with respect to o, where o is the center of the rotating frame. We know VA with respect to O is V1 and VA1 with respect to O to be V1 prime. So we get from this equation VA with respect to A1 is equal to V1 minus V prime. Similarly, for a point A prime on the larger disk, we get velocity of A prime with respect to A2 is equal to V2 minus V prime. And these are the directions for the new frictional forces. So, we have here V2 and here V1. So this vector would be minus V1 prime and this vector would be minus V2 prime. And the new frictional forces would be F1 prime and F2 prime. So parallel transporting these vectors from A2 to A1, we have here V2 minus V2 prime and F2 prime, as this vector here is nothing but VA with respect to A1 and this vector here is VA prime with respect to A2. Now, the torque due to the frictional forces will accelerate the smaller disk, which means omega will vary. So as long as omega is less than capital Omega, there will be frictional torque. Now what if we take omega to be equal to capital Omega? Let's see what happens. So previously we found VA with respect to A1 to be equal to V1 minus V prime, which could be written as OA1 cross capital Omega minus O prime A1 cross capital Omega. Now we can further write it as OA1 minus O prime A1 cross capital Omega. And this position vector is nothing but OO prime cross capital Omega. Therefore, VA with respect to A1 is perpendicular to OO prime. So VA with respect to A prime is always perpendicular to OO prime. Similarly, V A prime with respect to A2 is always perpendicular to OO prime. So if the velocities are perpendicular to the line joining O and O prime, the centers of the larger disk and the smaller disk, and the frictional forces are also directed perpendicular to OO prime along the direction of motion, and the net torque about O prime, center of the smaller disk, would be, so tau is equal to L2 prime F2 prime minus L1 prime F1 prime, where L1 prime is this arm and L2 prime is this arm. Therefore, this equals I alpha, where I is the moment of inertia and alpha is the angular acceleration. We know omega is equal to capital Omega, which is a constant, hence alpha is equal to 0. Therefore, we have L2 prime F2 prime to be equal to L1 prime F1 prime. Now from the diagram, we can see that L1 prime is equal to L2 prime. Therefore, F1 prime is equal to F2 prime. So the net torque is equal to 0.